It was going on, guys. Qemu here. We're running into a very exciting part of our operating system development. So from now on, we can develop boot sector game and apps under GameOS, believe it or not. So how on earth is that possible, you might be wondering, when we are limited to 512 bytes of the size of the binary executables, and how actually to develop anything, how to write the code? Well, the answer is pretty simple. We can write directly in machine codes, in x86 machine codes. And in order to do that what we need, we actually need a tool allowing us to input the bytes directly and store them to the memory. And then we need additional command to run the code that we've stored at some other place in the random access memory, to just to jump there, literally to make the code segment being there, make the instruction pointer point into the very first instruction out there, and then processor just runs instruction by instruction, and eventually we just drop back. So that's kind of pretty it. So I would demonstrate this in an emulator and on the real hardware as well. Well, even though I still the quality of shooting my real laptop is not really that great, but anyway. So let's start with demonstrating the. Let's start by demonstrating the improvements, let's say. So if I just say run.shell. So here, by the way, the list command has been improved, so now it doesn't like clear the screen. I feel this more like I don't know, like how the shell should look like, basically. And the app that I've developed yesterday basically is called Edit, and what it literally is, it is a hex editor. So the entire source code, before I just get into the demonstration, just want to show something I'm really excited about. So it hardly fits into 512 bytes, but eventually it does fit there, actually. So if we just, let's say, open a new tab and say xxd and edit.bin. So just to give you an idea, so here's the native Linux hex editor, by the way. So here is the source code for my hex editor, and you see like only 2 bytes at the very end are free, but those could be the like boot signature bytes. So yeah, it's quite pretty full of bytes, to say it least. So yeah, it was because of that we have some limitations in terms of how can we edit the memory, basically. So first, initially I was going to implement the backspace, but then I realized that if we can do the direct memory addressing, so like first we input the address in memory, in random access memory, where exactly we're supposed to be writing the bytes to. This is gonna be more like universal thing, because we can just like override the bytes at the same address if we specify that sort of an address. So currently, the way it works, it just this address, so 7700 hexadecimal in the random access memory, that's slightly below the boot sector and the stack. By the way, we have a free zeroed memory for kind of like writing our application in x86 machine codes. But before writing an application, so we're going to be writing the actual application on the real hardware to make it hardcore, right? But here I just want to show, I just want to introduce the functionality of the editor. And so let's say I want to write a single byte right over here. So the byte is represented by 2 digits, okay? So I say 70700, and now it has just initialized the address of where we're supposed to be writing into. So what happened under the hood, the DI register now points to hexadecimal 7700, okay? And now let's say I want to input byte 97, which stands for ASCII character A, right? So if I do this, I have this byte being written. So let's say I want to enter the next one. So I can say 7701, and let's say I want to put there like FF, okay? I'm sorry, not 00. Oh, sorry, it's not 01, not 10, but 01. So 77. Yeah. By the way, this 10 is just like. So we have 16. So we have 16 bytes here and 16 bytes here. 1, 2. Hold on a sec. 1, 2, 3. Yeah, but 32, about 32 digits here and here. So eventually we have 64 digits. Yeah, by the way, the reason why, so yeah, let me just fix this. So 7, 7, 10. By the way, how can we fix? So let's say I put this into the wrong place, right? So I can say the same address and put zeros there, and I've just erased them. That's the way how to do this stuff. And now let's say 777 MN01, obviously. And let's put FF there. And now it just goes right into the place. And now if I, if I hit enter, I need to enter the address kind of like from scratch. Yeah, but let's say I go to the next line. So let's say 7720. And I can input bytes like this, right? I can input bytes like this. I can even input bytes like this. And all the bytes getting written, so it ignores the spaces, right? So you could just put the bytes wherever I want to. And let's say also what is possible, so if I go to, okay, I just typed the wrong address, so I just type whatever address, and then I can press escape, because I just hit wrong address. Not the most handy way ever, but anyway. And if I just go back to edit, all the data is there because it's just in the random access memory currently, all right? So let's start again. So I want to say 77700, and now let's say I just want to add the entire program, okay? I don't know, I'm just putting some random hexadecimal values. It doesn't matter really what in particular am I doing here. So I can go to the next line and whatever, and this was a bit wrong, but well, anyway, it doesn't matter really. So it just goes, yeah, this is the user string, and here, yeah, and here it just inputs the data. So yeah, if I did put something wrong, I can just manually calculate the address, the offset for that byte, and replace it by hands. So somewhere here, well, I hope you get the point. So we can just type the entire program without kind of line breaks, without hitting enter. And again, like if we say want to type some byte here, so let's say we're so cool encoding machine codes that we know that we have a certain byte, certain instruction that we want to change somewhere in the code. Something like if you see the code, you want to change some instruction here and then reassemble it again and run. That's something similar. So we can just simply say like 77 and C0, let's say plus 16. So in hexadecimal would be 10. So just to calculate the offset, so 77 C0 plus hexadecimal 10, which is 16 in decimal, 770. So to type a byte here, again, like 770 D0, and I just put a byte there, and here we go. Okay, so I got a byte here. So I can replace it, whatever. And then in order to run this stuff, I can just escape. And if we list again, we have this new run command, which is that simple. I'm gonna be making extended tutorials, very detailed tutorials on how to make this hex editor. That's gonna be the topic of the next few videos. By the way, But just to give you a rough idea, so how the run works, it's very simple. It literally jumps to the location where the program is. But if I do it now, nothing is gonna happen because this is just the random bytes I've entered. So to give it a bit more of a sense and to show how this works on a real hardware and how can we actually code a real application under GameOS in this real mode of x86 processor. I've created, so yeah, let's get out of here. So I've created this hello.asm file, and what it does, it just prints hello, the new line and the carriage return, and then jumps back to the shell. That's pretty it. So not the smartest way of doing things. I'm sorry guys, I just didn't wash my face today even. It's just too early in the morning and I'm already shooting the video. Okay, so I could have obviously make something like print string function, right? Like this one. And maybe it even takes less bytes, but it's not the case. So the point is that I just wanted to demonstrate the bare kind of machine codes, and in order to be able to reference the certain variables. So the variables from the machine codes perspective are just the addresses in the random access memory, and bearing in mind the fact that we jump to a different segment, so we need to adjust the data segment. And again, like as far as it's not really that easy to debug currently. I didn't really wanted to get bothered with that. But that's about the next experiments, let's say. And by the way, I'm absolutely serious in terms of planning I'm absolutely serious in terms of planning a series of tutorials on how to code in machine codes. And I'm gonna be using GameOS for this sort of a purpose, and this is gonna be possible to follow online because of the online emulators that we have. So anyway, without further ado, let me just show you how the assembled hello bin looks like, and this is how it looks like. And we can't even run it here because it's not a part of a project. It just I just needed the machine codes, so these bytes. Okay, so we'll now enter these bytes on a real hardware, hit enter, and this would execute, and this would result in printing the hello string and going back to the shell, believe it or not. So are you ready for the show, guys? So let me just turn on my wife's smartphone. You still see me, as probably it's not the best ever way. Yeah, probably sit something like this. So let me turn the camera a little bit. Okay, so yeah, you would be seeing here in this window. I'll make some video editing later on. Okay, so all right, so here we go, and let the show begins. Okay, you now already should see here what my wife's smartphone is showing. Okay, so let's start the computer. This is another one, my good old Asus laptop, and we boot into GameOS, right? Okay, so let me adjust this autofocus because yeah, for some reason, I'm sorry guys, this is weird thing because, okay, now finally works. Okay, so same thing, so same operating system, so we can list the files. Yeah, we can even still play a game of bricks here. Okay, but no time for games, and we go for coding in machine codes. And I don't know how about you guys, but I think that on the real hardware it looks really cool. Okay, so now a CodeMonkey job, something that I've been up with when I was a kid. So just seeing some codes on screen and type them to somewhere else without much understanding what they are doing. That's pretty all about my programming career, by the way. So let's enter them one by one. So we want to start with the address 7700. So I type the address 7700, and then this byte. So B40E, B40E. I can make space, I can not make space, it doesn't matter. B40E, B048, B048. If I don't type this correctly, I would just restart from scratch, because even though it's possible to fix, as I've been mentioned, but calculating the proper offset takes ages, so it's really easier to start from scratch. That's just from my experience. So CD10, and you'll notice that codes are repeating from time to time. B40E, B40E, because of this bias calls, interrupts. B40E, so we got 4. Okay, B065, and this already feels like letter H is gonna be, probably, maybe not, I don't know. B065. Okay, CD10, CD10, and B40E, B40E, and B06C, B06C. And I can hit enter here, and we have, you see, like here, we have exactly the half of the string, let's say. So now I can set the offset to 7710. Okay, and from here on the desktop, oh guys, you just yeah, the problem is that I can see the codes here, but you will see the video overlapping on this screen, so you won't ever be able to see what the codes that I see, but you see that before I started this. So anyway, so trust me, these are the codes. It's impossible to memorize them. So yeah, CD10. Okay. Okay, B40E, B40E. All right. B06C, B06C, CD10. I forgot to put the space, but it doesn't matter, it still would be working, so no worries. So CD10, so I've entered 4, and now again next 4, so B40E, B40E, space 606F, oh sorry, B06F, B06F, CD10, okay, and B48, B40E, I'm sorry, B40E, and now it should fill right over in here, so the rest of bytes. So now the line is complete, and we have B40E here at the very end, and this is what we have here. So 2 lines here. Okay, you just can't see the hex editor, so yeah, let me actually make it. Hold on, guys. Just really want to show you. So new window. Now you should see it. Yeah, it's a bit of a pain because just want to make the fonts like, I don't know, let's say like this. Wasn't a good idea really. Okay, let's drop back. Well, okay, just doesn't matter. It doesn't really matter that much. Yeah, I just wanted to say that, well, I still no place to put it. Oh, okay, here is yeah, how we can do with this. Okay, so hello bin, yeah, now okay, awesome, now it's perfect. Now you can see the codes that I'm typing in. So we've just typed this, this half of the line, and it's just the half of the line here, and then this one is the next half of the line here. All right, I mean this one, and now a few bytes at the very end. So we have this offset 20, so I just add this 77 here, so I say 7720. So now I would be typing here, okay, and this is what I've been doing, that you can see because of the video there. So B00A B00A space CD10, okay, B40E, okay, B00D, okay, CD10, EA00, EA00, and then 4 zeros, 0000, and then 08, and we are done. So our hello, not hello world, but I would rather say hello app, is now should be okay. And now I just press escape to go back to the shell. Now the commands are still available. And by the way, yeah, if we go back to the editor, we can fix something if you want. So here is the 8, by the way. Okay, so now in order to run this, I need to type run. So yeah, so how do I know this? Because of this list command. Yeah, now I can type run. And now what would happen after I click enter? So the instruction pointer would start pointing to this address in the memory and would start executing these instructions one by one. Okay, so here we go, we got hello. Can you believe it, guys? I know, this is really awesome. We can execute it again, and because of the fact that it just jumps back to the shell location. So we have a look at the memory map. So yeah, here is the location, here is the shell location, and it just jumps here. Okay, so that's the reason why I find myself back in the console. Well, obviously, if you do something horribly wrong in the editor, then it would just stuck, and I don't know, everything would get broken. But I don't know, I think this is a proof of concept that it's actually possible to develop games and apps under GameOS using this fantastic hex editor that fits only 512 bytes, and it's pretty usable. You know, like the most cool thing about this is that it's really usable. So yeah, you don't have delete, but you can actually type to whatever memory cell, and you can overwrite to whatever memory cell. And I personally find this to be really awesome. Okay, guys, so I just stopped the video here on the smartphone. All right, and just a few words. Okay, yeah, finally managed to come up with a more or less decent lighting there, because yeah, otherwise it was really awful in my previous attempts to record it. So again, like yeah, in the next few videos, we're gonna be implementing this exact hex editor. We're gonna clean up the list command a little bit, and just a few words asking some questions you potentially might have arisen in your heads, basically that how to store your work, right? Because this editor writes directly into the random access memory and executes respectively from the random access memory as well. That's pretty clear. But how to store it? So just like we can read the sector from the USB flash drive and upload that sector to the random access memory using BIOS interrupts. Exactly the same, we can do the opposite. We can specify the certain address in the random access memory and then write that address to a given sector on the USB flash drive. And if we do that, then the next iteration, when we open our list command, when we use our list command, we should see a new binary executable appears. And during the development, here I want to introduce a bit of an issue that I didn't yet, that I don't know yet of how to properly kind of like resolve it, to be honest. But well, anyway, so in this low level stuff, it's really important where exactly the app is running. And like in assembly, if we just do if we use this kind of labels, right? So let's say, depending on the offset of where exactly in the memory this program runs, the values for these labels vary, so they become different. So if I take this exact code and try to run it not in the boot sector but somewhere else, okay, this code would still initialize the data segment, which is pretty awesome, but the assembled version, the binary version, would be different, because these are literally the addresses. So they take the origin and just add all the bytes being spent for instructions, and then whatever we have here is the actual physical address in random access memory. Okay, so if we change the origin, so even though the data segment would be adjusted properly, still these values would be different. So I just want to say that it's the case where the assembly source code might look exactly the same if this piece of code runs in a different physical address in the different physical addresses of the random access memory. So it might look the same, but the binary executable would be different because of the actual address. Because of the actual address shifts. That's a bit of an issue. So how can this affect the development? So if we're going to be loading those executable as we usually do, they would get loaded into the boot sector, and this is not going to be working because of the run labels. So we can either not use labels there and produce weird code like this, which is not the case, or alternatively, I don't know. So it's still something to think about. So I just wanted to make this proof of concept, like being able to input the bytes and being able to jump there to like implicitly adjust the instruction pointer and just run the code. And this works, but I still need to think about how this would actually be working. So we can definitely store this program that we've encoded in binary to the USB flash drive, but well, this program would run regardless of sector, because it doesn't rely on any labels. But if we do want to have some labels, then that would be a bit of an issue. So maybe there would be just a different coding style, not involving this offsets. And another problem again, like, so if we specify the offsets from the boot sector, it's not going to be working as well, because the boot sector is always busy by executing the current command. So let's say if we're working with a hex editor, so hex editor in the boot sector currently, and if we do reference the boot sector addresses, that would be referencing not the app's addresses, but the editor's addresses. So that's a bit of a pain as well. I'm not sure how exactly I'm going to be resolving this, but as soon as I come up with a decent solution, I think we'll then just start coding this, or probably we'll even start coding this first and then we'll need to rethink a little bit how this works. So probably, I believe that the easiest way is just to adjust the shell. So, it would be different, so running bundled games and apps would be happening within the boot sector, and user-defined games and apps might be running in this newly defined sector of 7700, where this code starts. So maybe that is the case. I don't know. So that might be the case potentially. So I just need to test this to see how it works, and then we'll see what we can do out of this. Okay, guys. So this is it from my side. Happy coding in x86 machine codes. So tutorials on that sort of a thing are coming soon as well as these tutorials. So we're gonna be having some fun times, so feel free to join, and I would be pleased if you do so. So this is it from my side, guys. Thanks for watching. Until next time, and take care.